Welcome to the first lecture in class. This lecture will cover the Introduction to Data Visualization. Data analysis is defined as the task of transforming, summarizing, or modeling data to allow the user to make meaningful conclusions. Data analytics supports the transition of data into information and the development of information into knowledge, which drives decision making. Data analysis can really be broken down into several main branches, from descriptive statistics, inferential statistics, exploratory data analysis, and predictive modeling. Descriptive statistics describes the distribution of data. We may use measures such as the center, which is the value that frequently occurs and can be measured through the mean or median. If we move over to the next branch, there's inferential statistics, which refers to methods with the purpose of reaching conclusions that extend beyond the immediate data alone. This is where we typically use methods of inferential statistics, such as t-tests, linear regressions, and ANOVAs. Exploratory data analysis is the next branch, and this is really a data mining technique where the intent is to uncover patterns in the data. Now, graphical techniques are typically adopted to uncover those patterns. For instance, we may use things such as box plots to identify any outliers in a data set. This is the space where we will live for this course. We will examine ways of exploring data using data visualization methods. Next is predictive modeling. It's another data mining technique where historical data is used with machine learning algorithms in order to train the algorithm to predict the occurrence of a target variable. These models are used to predict outcomes, and the models then can be applied to new data sets for prediction purposes. When we consider the purpose of exploratory data analysis, the main reason to adopt an EDA approach is to answer the question, what is going on here? That is, EDA can help to identify trends and patterns in the data to obtain information and knowledge regarding what is happening with our data and within an organization. For instance, EDA can be used within an organization to monitor the number of readmissions over the period of a year. If there is an uptick in readmissions within a certain time of the year, further investigation may be warranted to identify what is going on here. The uptick may be related to an outbreak in a particular condition. This may lead to a decision to offer more educational resources or implement a program to assist in limiting readmissions when data indicates a future outbreak. EDA is meant to offer an understanding of the data without having to draw formal models or a hypothesis, which is done in inferential statistics and data mining. Patterns in the data are meant to illustrate stories and are the hallmark of EDA. When we break EDA down further, a critical element to the EDA process is to visualize data in order to clearly see trends. Data visualization refers to the depiction of a data in graphs to help identify outliers, detect trends and patterns, and potentially suggest future hypotheses for formal testing. Oftentimes, we begin an analysis with EDA, adopting data visualization techniques, and then move into inferential statistical methods and or even data mining methods to determine if the trends are significant or to predict future occurrences of such trends. If I were to ask you to choose the visualization method displayed on the screen that does the following, which of the two options would you choose? The first question is this: what visualization method, either the table or the graph, leads to a more accurate interpretation of a value? The second question is, what visualization method leads to a more rapid interpretation of a value? Is it the table or is it the graph? So let me say the first question again, and let's consider this for a moment. The question is, what visualization method, the table or the graph, leads to a more accurate interpretation of a value? Consider this for a moment. If you had to choose the precise average daily sales for the month of May using just the graph, How would you do that? Well, let's talk through the steps. First, you would have to find the month of May on the graph. Then you would have to find the value for the average daily sales. So you'd follow May and go up until you hit the line. Then you'd find where that point is on the line and follow the value all the way to the left to detect the discrete value. Now we can say it's about $14,200. However, try to do the same task with the table. Again, choose the precise average daily value for the month of May. Using the table, you can quickly find that in May, the average daily sales were $14,513. Not only did the table lead to a more precise estimate for this task, but this type of task of obtaining a specific value was faster with the table. So that really answers both of those questions posed. With that specific task, the table is more accurate and it's faster. Let's look at the second question again. What visualization method leads to a more rapid interpretation of a value? Now consider this for a moment. If you had to choose the month with the highest average daily sales, and you attempted to do this with the table, how would you do that? Again, let's walk through the steps. First, you would have to go through the list of values one by one in the table and rank the values in your head. This is incredibly difficult to do. Instead, if you were to do the same task using the graph, where you had to choose the month with the highest average daily sales, you can quickly see on the graph that the line at the point where it is for November is the highest. Therefore, you can quickly see that November has the highest value for the average daily sales. So therefore, when the task requires you to specify a pattern in values, a graph is typically more accurate and faster. Now you'll notice that the right answer to both of those questions posed really depends on the task of interpretation that is required. Throughout this course, you will be challenged with a similar scenario, and you'll have to consider what is the best visualization method. When considering the best way to visualize data, it is also really depends on the type of data you're working with. There are really two major types of data. There's qualitative and there's quantitative. Qualitative data can be categorized and summarized, but there's no real natural numeric values. It can take on two main forms, nominal and ordinal, where nominal data falls within discrete categories that don't have any apparent natural order. For instance, an example would be gender. Ordinal data falls within discrete categories, but it can have inferred order to it. An example would be age groups. Now, quantitative data is naturally numeric and take on two main forms. There's interval and there's ratio. Interval data, it's numeric, where the distance between the two values has meaning. But if we were to multiply those values, it no longer has its meaning. A common example is temperature, where you can look at a temperature and it can take on many different values, and two temperatures can be compared. Also, if we look at a value of 0 for temperature, this doesn't have an interpretation. Now let me take a step back and explain that. A temperature of 0 degrees Celsius is cold, right? We can make sense of that. But that does not mean that it is the absence of temperature. Ratio data, on the other hand, 0 has meaning. And values for ratio data, they can be doubled or multiplied by a constant, and they can still retain their meaning. An example would be currency or length of stay. Now consider what a value of 0 would mean for currency. It means you don't have any money. Therefore, it carries meaning. Additionally, quantitative data can be discrete or continuous. Discrete data includes just a limited number of values, whereas continuous values can include any number. So those are typically values that can have a decimal place with numbers listed after the decimal. Now here's a basic chart that shows a breakdown of the two types of data and their subclasses. Now as shown on this figure, quantitative data can be continuous, meaning it can take on any numeric value. Discrete quantitative data can take on a limited number of values. Discrete data, they have finite values, or they have buckets. You can count them, for instance. Continuous data technically have an infinite number of steps, which form a continuum. The number of questions correct would be a discrete value. There are only a finite number, and it's countable. You can count the number of questions. The results from a laboratory test can be continuous and take in an almost infinite number of values. Now this table offers some assistance in identifying the various data types. Nominal is discrete data that can be sorted into categories and not on a numeric scale. Ordinal data is discrete data that has positive values only and can take on an integer value if it's coded as a number, or it can take on textual values. Interval data, it's typically continuous. It can be positive or negative, and it takes on a numeric measure. Whereas ratio data can be continuous. It can be positive or negative, and also is a numeric measure. Another component to consider when looking at data types is to determine if the data you're working with is unstructured or is it structured. Unstructured data can take on any value and has no inherent organization or structure. Typically, the data is textual. This data is often captured in an open text field. For instance, when a clinician writes a clinical note, the text used in that note is at the discretion of the clinician, and the clinician uses their own words to populate the note. There's no inherent structure or organization to the note that would allow you to describe the data easily. Structured data, on the other hand, has organization and structure. Structured data generally consists of numerical or categorical information, and it is objective. It simply is data that exists. There is no additional interpretation. For instance, their blood pressure, sex, and weight, they're all structured data elements. You can easily interpret the value. Let's consider the impacts of structured and unstructured data when considering methods of data analysis. Now, structured data can oftentimes be analyzed by counting how often certain events occur, by calculating means or averages, by looking at medians, examining the standard deviation, etc. Unstructured data, however, cannot undergo this same level of analysis, at least not right away. When working with unstructured data, we must add structure to it to work with the data. For instance, we may need to count how often certain terms occur in a clinical note, such as the word hypertension. This can cause considerable challenges, however. If the text hypertension is found within a clinical note, does that mean we can infer the patient has hypertension? Well, maybe not. The reason is that we need to understand the context that the word was used. Hypertension in a clinical note may be referring to a family history of hypertension. On the other hand, it may be referring to a patient having the diagnosis of hypertension. This is where the use of natural language processing, otherwise known as NLP, was designed to overcome some of these limits and to help add structure to unstructured text by considering concepts such as context and syntax. Now, the type of data will also influence the methods of aggregating data. If we have categorical data that is nominal, we may only be able to count how often certain events occur. However, if we have ordinal data, such as survey data that is captured on a scale from not at all agree to very much agree, this can be summarized as a count, or an average can be conducted. Now, quantitative data is a lot more flexible, and we can adopt numerous aggregating methods, such as the sum, an average, the median, a count, the minimum, maximum values, standard deviation, and variance, and so on. The best thing to consider is if the method of aggregation makes sense. For instance, if I calculate the average length of stay for all my patients, does that make sense? Certainly it does. However, if I attempt to calculate the average gender of my patients, Does this make sense? Not really. It doesn't make sense. If I had an average gender of 1.5, what would that mean? Well, it wouldn't really mean anything, right? Instead, with gender, you can count how many males there are and how many females there are. Now, data analysis has some terminologies that should be understood. A data set is a collection of data. Oftentimes, a data set will have multiple columns and many rows of data. In a mathematical terms, this is referred to as a matrix, while in a database terms, this would be referred to as a table. The observations of the data set, they make up the rows of the data, while the variables make up the columns. Now, the dimensions of a data set, this is the number of observations or rows by the number of variables or columns. So in conclusion, healthcare is a data-driven industry that requires informed decisions. Data visualization is a type of exploratory data analysis that can offer insights into the trends and patterns of your data. The type of data can influence the type of visualization and also the type of data aggregation that you use. Throughout this course, we're going to be exploring these concepts further and get hands-on with creating our own data visualizations that ultimately are going to allow us to make more informed decisions with our data.